Hello, ladies and gentlemen. Today we're going to implement the lowly spin lock nearly from scratch. We are going off the beaten path. This will not be in any mainstream study guides like Grind 75 or Cracking the Coding Interview. This is implementing the most basic of synchronizing primitives using only atomics and no mutexes from scratch. All right, so we've got a blank coding pad here. I'm gonna go ahead and make our main function. This is absolutely required, and then we'll talk about the approach. So int main, and then int argc. That's the number of arguments that we pass from standard in, which I'm not going to use, but that doesn't matter, so it would just be 0. And then pointer to a pointer of characters. argv. argc and argv, those are just conventions. They can be named anything. And then return 0 for OK status. Back to the operating system. All right, so what is a spin lock? When you have multiple threads trying to access the same data structure, something that cannot be read by more than one thread at a time without causing runtime errors. And those runtime errors are called race conditions. And normally, at least in C++, you would use something like a mutex for mutual exclusion. But the goal here is to create our own mutex using the underlying elements without calling this directly. So what we need in C++ is something called the header called atomic. And this is pretty jack of all trades. So for example, if you've taken a class where they teach this stuff, they're usually going to use C instead of C++, and you're going to use a library called pthreads, and that's going to have all that stuff included here. But in C++, it's part of just the regular standard library. You don't need to install other dependencies. And then we're going to use atomic and a Boolean. So let's go ahead and make the template class spinlock. Now, what a spin lock does is it's the most naive form of synchronization. This is where when you try and, quote, lock it or acquire it in one thread, okay, it will get it. And then while it still has the lock, any other thread that tries to grab this same lock will spin and spin and spin and spin and spin and do just an infinite wait loop until the lock becomes available, where the first thread relinquishes it, and then the second thread can pick it up. The pros and cons of this are it's very, very simple. It's very naive. And then sometimes you have, okay, the reason you might spin, there's a benefit to it. If you were to have, say, a lock that causes the thread to go to sleep, or do a context switch where it would go to some other activity in the function, do something else actually useful with the time, well, if it would otherwise be a very short wait, well, that can be a waste because the work itself of context switching can actually be pretty heavy. And the more threads you have, the heavier it can be. And context switching is generally the way that you could have a program that, quote unquote, has more threads than your CPU physically has. So if you've got, an 8-core processor with hyperthreading that effectively gives you 16 physical threads, but if you want to do 100,000 threads, you can do it. Logically, it will work. It just doesn't make sense because you'd have these threads context switching, and you can only have your physical number of threads, so 32 in this example, active at any one time. And the rest will be context switched out. Anyway, so instead of incurring the cost of context switching, a spin lock avoids that because you never context switch away and you never have to context switch back. The downside is, well, if it's a long wait and the wait is much, much longer than twice the time for a single context switch, then you're losing out on valuable time. You could be doing meaningful work with that thread. All right, so we got a couple of things. First, let's define members. So classes by default have private elements, so I'm not going to declare private, but I am going to start declaring elements. So let's call, actually what I'm going to do here real quick is I'm going to use this using namespace standard. And the reason for that is it's sometimes good, sometimes not to use that in production. In toy examples like this and in interviews, it saves you having to type this over and over and over 1,000 zillion times in your code. So it's just that little bit of time saving. So atomic, and I'm just going to make it a Boolean because that's all we need. And I'm going to call it latch. Now let's make our constructor public constructor spin lock. And what it's going to do, it's going to take no arguments, but it's going to initialize this latch to false. As in, you create the lock, it's going to be unlocked from the get-go. So that's fine. So that's our constructor, and that's all we need there. All right, so there's two main things you do with something like a mutex, or in this case, a spin lock. And it's going to be lock and unlock. Doesn't need any arguments. All right, lock is the more interesting. So let's go ahead and start with what that does. We need to acquire this latch. Now, I'll start with the naive approach where, let's say, if not latched, then set latch to true. Otherwise, or so if not, instead of if, let's say while. So while the latch is locked, we're going to wait. And then once we have it, we're going to grab it. All right. So this is not going to work, and I'll tell you why. So when you get into multi-threading, okay, let's say you have several threads call lock at the same time. What happens? You're going to have, okay, the first thread, while latch, so while it's latch, the check's going to be false, and it's going to proceed to this statement where it would set it to true. But what you have happen is, okay, if you have many locks, many threads going at the same time, contesting for this lock, what you can have is multiple threads will make it through this check, more than one by the time, and then, so you have 2 or 3 or 4, however many threads pass this before the first thread has a chance to actually set this to true. And so you get a multiple threads thinking they have the latch, and that becomes a race condition. So you need to do 2 operations. You need to do the conditional check and the setting at the same time. You need that to be one atomic operation. All right, let's talk about the solution for that now. You need to do 2 things at the same time. Walk and chew gum. So what happens is you have this latch, and it has the member functions. Most of them are overloaded, so setting it, unsetting it, those are things you'd expect, and because it's atomic, they're overloaded for the equals operator. So this is, you'll see a set function, so set, or store in this case, store, this is equivalent to this. So those are the exact same thing. They're overloaded underneath the hood, so they do the exact same thing. Now what happens over here, we need, okay, there's, particularly for a Boolean, there's not as much going on. There's, regular setting and unsetting. And then there's these 2 functions, compare exchange strong and compare exchange weak. Compare exchange weak. It's not giving me autocomplete. Hold on. Compare strong and then compare exchange weak. So what those do is exactly what we need. They do 2 things at the same time. But they have some subtleties. Compare exchange strong is what you expect. When it succeeds, it succeeds. And when it doesn't, it doesn't. What it does is it takes a couple of inputs. It takes an expected value. So for example, compare exchange. It takes an expected value of a Boolean, because the underlying data type is a Boolean. So the first argument is expected. And this, okay, here it's finally got the tooltip. Expected, and the second argument is what you would want to set this latch value to. So it's going to compare these two things. If latch is equal to the expected value, then you set latch equal to the second argument, which in this case would be, we want to set it to true. Did I spell that right? Oh, it's because of these that's giving me twigglies. And if it's not equal to the second value, because of the way processors tend to work, where they'll come up with instructions in parallel and then just throw away some of the work if it turns out to not be needed by evaluation time. There's an under the hood reason why these functions must, so if latch is not equal to expected, then it sets expected equal to true. So it'll change one value or the other, either latch or expected. One of those is getting set to true, and that is determined by if these two are equal. So if we do not acquire the lock, we have to remember to reset our expected value. Expected equals false. And since, yeah, so expected is false, we're just resetting that each time so that it's always back to false by the time it gets put into here. And since we're having different threads, this is declared inside of the lock call. So this is thread private, meaning each thread has their own copy of this expected value. So we don't need to synchronize it. The only thing we need to synchronize is this latch, which is going to be shared in between the different threads. So that has to do with the scope. Okay, and then the third argument is not as, it's optional, and it defaults to a safe value. So intuitively, what you'd think about these atomics is that their memory order is called serializable. And that's a very, very strong memory safety guarantee. Serializable meaning if one thread does an operation and it starts first, it'll finish, and then the second thread tries to do an operation on it, it will see the value as if the second thread fully finished its operation on this latch first. So the first thread starts and finishes what it's doing before the second thread gets to do anything. But we can weaken that. We can weaken that guarantee in exchange for a little bit of speed, and it's called memory order acquire. And what this does is it prevents the compiler from reordering reads and writes within this function. So like reads will have to happen first before writes. It's not, so like if you got things below, it's not, the compiler's not going to suddenly put them before this call. So that's what that is. And the difference between strong and weak is weak can sometimes have spurious fails. I don't think it has spurious successes, but it will have spurious fails. But it's faster in general. So in a case like this, where it's a spin lock, we're spinning, checking this multiple times, you get that much better speed at the cost of a couple spurious fails, but that's fine. We'll just do another iteration of the while loop, and that will wind up being cheaper computationally than doing compare exchange strong, which has no spurious fails. So the main difference between compare exchange weak versus strong is strong you would use in just a regular if condition. Weak you'd want to use in a loop. So in this case, we're doing a spin lock with a while loop, meaning we want to use the weak version. And we have memory order acquire because, well, the way that I remember it for this case is you're trying to acquire the lock, so that's the memory guarantee you need. You could leave this out and it would be computationally correct. But throwing in this fine-grained control of what memory guarantees you want, that will make it a little bit faster. So we no longer need this because it's covered by this compare exchange. So a thread's going to enter. It's going to try to grab this lock. It's going to create its own private copy of the expected value. it's going to do this compare exchange weak in a while loop, and it's going to keep spinning, spinning, spinning until latch and expected are both false when they're compared to true, and then it will break out of the while loop. So actually, let's do. I need a not sign in there. Okay, almost. Yeah, there we go. So then it will break out of the while loop when these do not compare equal. So if they're not equal, it will set expected to true, and it will return false from this call. So we need to invert that there. And I think that's it for the locking mechanism. And the unlock is much, much simpler. It's just simply, you know, you don't, as long as you don't call unlock from another thread, unless you mean it, you're generally, you're just setting it false. So latch equals false. But we can do a little better. All right, so we talked about memory order here. Now this is equal to, let's see, it's equal to store false with a guarantee. So let's bring that out. Guarantee. So memory order what? I think is it one of these? Yeah, sequential consistency. So these are equivalent statements here. Sequential consistency. But we don't need that. We can go with a weaker memory guarantee in exchange for a little bit of speed. So memory order release. So that's our unlock function. And that's all we need. So what I'm gonna do is test it out. So that's the algorithm. If you want to stop here, then you won't have missed much except for going through the testing functions. Let's go ahead and create some cases. So I'm gonna do I want to do, this would be the easiest. It might be, I don't know if this is right to use in an interview setting. It might depend on the environment and if they have this enabled. So this is called OpenMP, and it makes it very easy to make parallel for loops, basically. So we're going to have for however many threads we want. Actually, do I want to? Yeah. So if I equals how many iterations do we want to do? I'm going to make first some counter. So count int. I don't know that, and we're going to declare this the spin lock. I'm going to call it, I don't know, just lock, and it starts out as unlocked by the constructor. We got our counter. It is not thread safe. And then we are incrementing it. So however many times, let's say, I don't know, a million, billion. Some big number. Let's do a big number we can keep track of. We want it to be clean so we can eyeball if it worked out or not. All right, so there's our loop. And I haven't made any threads yet, but that's okay. So let's do the critical section. Lock. That's our lock method here. And we have our lock.unlock. Now what do we do in between? We're incrementing the counter. And then that's it. I think that's our critical section. And in this case, I think that's it. So I'll just print the output. So add the IO stream header. IO stream. And then we have our counter value. Okay, so how do we actually make the thread? What I'm going to do is use OpenMP. Pragma. OMP parallel for. And then shared is going to be this lock. So, and then the counter. All right, so those are shared, and I think everything else would be private by default unless I specify. Which, yeah, there we go. So this is going to use by default however many threads I have as a hardware process. So I think my PC has, I don't know, it's somewhere between 10 and 32 or something. Whatever, it's several threads. And let's go ahead and run it and see what happens. What do we get? Did it run? Did it run? No. Run. Did I make the number too big? Okay, it's pretty even. So what happens when I don't have this while loop? So let's go ahead and not do this lock and unlock. I'm gonna shrink that a bit so it finishes quicker. I'm looking for it to be some crazy number. And so maybe, you know what, I don't think I have OpenMP enabled right now, so I'd have to add it to my flags. What I'm gonna do instead is I'm gonna use a thread pool. So let's go ahead and do that. So task. And this is gonna be a, I'm gonna pause and I'm gonna set up my thread pool and then I'll be right back because that's not the point of this video. If you're curious how to enable OpenMP, you have to include the header, but you also have to add it as a linker flag. So this is the lines that I added in CMake. So finding the package and then adding linker flags. And this is not something you'd have to know off the bat. Just Google for this, basically. If an interviewer expects you to know this offhand without just looking it up, that's a major red flag, and you should reconsider if you want to work there because that's very esoteric. Yeah. Anyway, so here's our result. I have no synchronization going on, and the sum is all over the place because it's not thread safe even a little bit. So now let's try adding in the lock. Taking a lot longer. Taking much longer. And you can see our number is nice and round and clean. So let's speed that up a bit. Yeah. Every time consistent, it's the right number. Okay, so let's talk about pros and cons some more of spin locks. So we talked about context switching and the cost. Another issue is fairness. So spin locks, they give the lock to just whoever comes, first come, first serve. You want it, you got it. Oh, next guy was too slow coming back around for his next iteration of the while loop. Oh, that's too bad. Maybe next time, buddy. So there's a whole sequence of other types of locks you can do that add things like fairness. Like, for example, a ticketing system of, you come for the lock and you grab a ticket number, and then when it's your number, then it's your turn to get the lock. And if it's not your number yet, then you don't get the lock. Or you could do something like a circular queue, which is, you grab a place in the queue. The queue would have to be at least as big as the number of physical threads that you have. But that would be, it'd be fair, it'd be quick. You know that you're never really going to have more threads waiting in the queue at any one time than you physically have. You could logically have more threads than that, but it's going to work itself out in the details. Or you could try and save on your space complexity a bit and use a linked list based queue. That one's called like MCS. And that one is got some subtle issues. It's it's tricky to implement. There's some corner cases you got to think about to make it actually work in practice. But in that case, you save on space because you have no more nodes in your linked list than threads that are actually waiting for the queue. And then your maximum is still expected to be the number of physical threads that you have. You're probably not going to have more than that waiting on this linked list at a time. And that's it. That's the end of the video. Spin locks. So we tested it out. We used, okay, parallel OpenMP is our thread pool maker of choice because it's a nice, easy one-liner to turn your for loop into a parallel for loop with the multiple threads. Or you could go with a simple task, not simple, conceptually simple, but trickier to implement task queue, where you then have to guard this queue and you have the threads circularly come and grab things from it. Um, if you have this available, use this for testing. But if you're getting into doing stuff like this in an interview, even if you just know the concept, they're probably not going to expect you to run it. They want you to mentally step through because these things are very finicky to set up. And that's enough pep talk for today. You folks have a beautiful, beautiful evening.